Okay, so we're going to talk about programming, and we've been thinking about this issue for more years than I care to remember. It really is about 35 years. That Seymour Papert and his colleagues at MIT had this brilliant idea that programming a computer could be a way to think about mathematics. I'm going to say a little bit more about that later on. So we're going to give you a snapshot of 2 or 3 projects that we've been involved in over time. And you'd be surprised that time doesn't really make as much difference as you think. I mean, obviously the technology has changed algebra recognition from what it was 30 years ago. And the access to technology has changed massively with some very surprising results. People, I suspect, practically, is there anybody in this room that doesn't have quite a powerful computer in their pocket or handbag? No. So that is a real change from what it was 30 or 40 years ago. But the issues are the same. The case for programming as a way to learn mathematics is the same, and we thought we'd give you a taster of what we mean by that. The first project finished, it must be 15 years ago. And the idea was that we would tap into the culture that kids enjoy so much, and that is playing video games. And what we tried to do was, first of all, say to ourselves, well, if kids have you ever seen anybody being taught to play a video game? It's a completely alien question. You just know. And there's a whole culture about what you do to find out. Wouldn't it be great if learning maths was like that? That you just didn't have to be taught. We also thought how important it would be that really, when you're playing a computer game, you're playing somebody else's computer game. The rules are not yours. You don't set the rules for the most part. Somebody else sets the rules and you play by the rules. But you don't take the rules and change them for your own pleasure. And that's a shame. We thought, wouldn't it be nice if we could turn people into producers and not just consumers of games? Wouldn't it be great if I wrote a game and sent it to Celia and she enhanced it in some way, sent it round to 2,000 people and they sent it back and so on. And we had that dream in the late 1990s, and of course it was unrealizable.
Didn't have the web.
Yeah, I mean the idea that you could post something up and thousands of people, even hundreds or dozens of people would respond, not just say, I love your game, I hate your game, but I've enhanced your game. And of course now it's a commonplace thing. Those of you who know Scratch will know that the Scratch website, unbelievably, has 10 million projects posted. 10 million. And the vast, huge majority of that 10 million projects is kids. And a substantial majority of those kids are not posting those projects because their teachers telling them to, although some are. They're doing it because they just love sharing what they've done. And those of you who have read the most important educational book of the last millennium, which is Mindstorms by Seymour Papert, exact reference from me over coffee later if you need it. Those of you who've read it will know that a very, very powerful way to learn is not just to build stuff, but to share ideas about the stuff that has been built. Here's a little girl who was 8 years old during the life of the project. She's now probably a great-grandmother. I've lost track of that. But she says a couple of very interesting things that I'd like to share with you.
Today I liked was because we got to show each other what we've been doing over the weeks.
So you like seeing what the boys have done, or what did you like about what they've done?
I like Triathlon's one because it was interesting and difficult, and it was easy to change.
We leapt out of our seats when we heard her say that. Interesting, well that's nice. Difficult, that's more than nice. It's not always that kids appreciate that something difficult is also pleasurable and nice. And easy to change. She was talking about the way in which we set up a way for kids to interact with the games and improve them and enhance them and share them and so so on. So when she says easy to change, she means, I think she meant easy to appropriate and make my own long enough for me to enhance the games myself. Now, of course, as I said at the beginning, what we would love to have been able to do is help her to share her games and enhance the process of game building across thousands or even hundreds of thousands of people. That was more or less impossible then, and now it's absolutely straightforwardly simple. That's a really big change to think about. And it's a change that we're not really exploiting enough at the moment in our classrooms, I think. Celia, do you want to say something before we move on? Okay, so here's the really almost insuperable problem about learning mathematics, which you don't have when you're learning about art, you don't have when you're learning about music, you don't have so much when you're learning about something tangible, something that you can build, something that you can touch. Somebody once said that mathematics is like a game of virtual reality without a computer. We have these incredibly abstract ideas that we have to try and get across to people, and yet we don't have anything on the whole that they can touch, anything that they can hold on to and pass to somebody else to enhance and so on. So I want to give you an example now of making mathematics tangible. We thought, perhaps we were slightly ambitious, but we thought like this. Let's take one of the hardest ideas that we know, that all kids find difficult. These are older kids than Najmina was. These are kids about 13 years old. And we'll take a really sophisticated mathematical idea that even adults would find difficult, and play around with it and build something for them to play with and make a very abstract, intangible idea tangible. So here's a question for you to think about. There's a number just a little bit bigger than 3. These, as it happens, it's quite a special number, but it doesn't matter. And it ends with 3 dots. What do the 3 dots mean? You don't have to, I don't want to embarrass anybody, but if you're sure you know, put your hand up.
Yeah.
Okay, well, what do the 3 dots mean?
Yeah.
Me?
Yes. Sorry.
Well, it means that, like in children's language.
Any
Okay, in
language,
children's
children.
language, grade 9, it means it's a rational number, means there are a lot of decimals, and you can't find a pattern, so you cannot put a dash and make it a periodic decimal. That's
Oh, so if you could find a pattern, you wouldn't put.
Pardon?
If there was a pattern,
yeah.
you wouldn't put the dots.
Me? If it's like
you.
that's how, yeah, me. If it's not a long pattern, I would put a dash. I
Okay.
wouldn't put it dots.
Okay. Yeah, one more.
Pi, or assuming they're talking about pi, doesn't end, it goes on. It's not a number that ends at 9265, whatever. and then
Right, but if
stops.
you didn't know that it was, I regret now making it nearly pi. If you didn't know, it just went on,
It's the
if you
first
weren't
step.
sure what was going to happen at the end, would you put dots?
For me?
If you weren't sure what was going to happen in the end, what would you still write dots underneath it? No? Okay, all right.
You would put
Interesting.
the last decimal. You would put dots and the last decimal at the end. That's how we explain our kids irrational
Okay.
numbers.
Well, I won't ask the next question, I'll tell you the next question, because the kids find it very difficult and confusing, right? So, we thought, it's funny, because kids do have an intuitive sense of what it means for something to go on forever. You dig a hole forever, I remember the little kids, dig a hole forever, you get to Australia, right? Well, where I live, you get to Australia, I have no idea if you get to. Let's take a different number. Anybody like to volunteer what sort of a number that is? No, you've had your turn. You can.
I don't.
No, I mean, why should you? It's a number. It might repeat. It might not repeat. It might look just like the first one. But for sure, the expansion, the decimal numbers do go on forever. But whether or not it's the same kind of thing as the first one is an open, I'm not going to go into the details. It's actually rather a different kind of thing. Let's take a number that probably should be really quite close. And that's 1/500. That's a very small number. And it must be quite close to 1/499, right? It goes on forever, probably, does it, or doesn't it? These are very deep questions. And I am sure that the one common factor between our two educational cultures is that it's very difficult for kids to understand. It's very hard for kids even to understand that as you go further to the right in a decimal number, the value of the digit gets less and less and less. That's very hard. We take it for granted, but kids don't. Well, we thought, wouldn't it be fun if we could write a programming language that would let you explore these kinds of difficult ideas? And we worked with somebody called Ken Kahn, who invented a wonderful programming language called ToonTalk, where it's on the web, it's free, and it's very outdated now. So I saw everybody reaching for their pen, but it's a historically interesting piece of work. But we're not advocating that everybody should go out and use it. But the interesting thing is that each of the computer science ideas that underpin the things that you need to do when you're writing computer programming, like repeating something until something else happens, like sending a message from one object to another object, is instantiated as a little animated robot. So you don't write a program, you instruct a robot what to do. You don't write a line of code that says, you communicate with you. I give you a bird and a little nest. You take the bird and put it somewhere, and the bird will fly to its nest holding any message that you give it. So this is a very beautiful idea, and I've come to the end of what I'm going to say to it, except I'm going to show you what happens when you look at 1/499. Now don't have a shock, because this doesn't look like any programming language you've ever seen before. So I take the number 1, I divide it by 499, and I get a great long decimal. Can you see the mouse?
Mouse is called banner.
Can't see, can't read a word, so we have to pump it up. And now I'm holding that number in my hand. Starts promisingly enough, doesn't it? That could be easy. Okay, now you notice it looked like I just keep pumping and it gets bigger and bigger and longer and longer and longer. And here's the really amazing thing, which is the point of this example. In principle, you can do that forever. You can have infinite precision on that decimal expansion. You can literally hold in your hand something that is infinitely long.
And you can walk along there and look at
And you can ask yourself questions that are unaskable unless you have a system of some kind like this. For example, how far along do I have to go before I find my house number? How far along do I have to go before I find my telephone number? That's an unthinkable question in a normal world. But I guarantee to you that each of our telephone numbers is in that decimal expansion. It's just that we might have to wait quite a long time to find it. So, again, I'm not saying that what the computer scientists call infinite precision arithmetic is the answer to anything particularly. But it shows you that if you have a new way of representing arithmetic, mathematical ideas, you bump into new kinds of ideas that weren't there before.
You need to show the multiply by. That's the answer. 1 divided by 499.
Oh,
Until
yes.
you multiply by 499.
How would you
what
check?
get?
How would you check that this infinitely long decimal really was 1/499? What would be a check for that?
Yeah, sorry, I'm just dodging in.
I didn't hear what you said.
Multiply.
Yeah, it should be that if I multiply by 499, I get 1,
Usually
And
it
not-
doesn't if you use most.
and not .999999997.
Show it.
I can't show it.
I thought you showed the next.
No. I do not.
Oh, right.
This is the bit where we're being married.
I thought you could.
You would have implied that we were married without us telling you. Yes, I could have.
You did.
Right.
So you've only got 4.